Today we are going to discuss a very important and latest concept about the environmental chemistry, that is the atom economy. Atom economy is a tool for green chemistry in order to make our environment green, in order to make our world green, in order to make our environment and world healthy. So the things are reversed towards the nature. So atom economy concept is very important in this regard. Cleaning up the environment and, more importantly, preventing pollutions are important issues in today's world. The theme for the 2002 National Chemistry Week is Chemistry Keeps Us Clean. While the chemical industry is traditionally viewed more as a cause than a solution to pollution, chemistry does offer unique solution in the area of waste prevention. One of the most fundamental of these solutions is the application of green chemistry principles of atom economy to chemical reactions. Atom economy moves the practice of minimizing waste to the molecular level. Traditionally, chemists have focused on maximizing yield, minimizing the number of steps, or synthesizing a completely unique chemical. Green chemistry and atom economy introduced a new goal into the reaction chemistry, designing reactions so that the atom present in the starting materials end up in the product rather than in the waste stream. These concepts provides a framework for evaluation of different chemistries and an idea to strive for in new reaction chemistry. As atom economy is an important tool for green chemistry, so it is important to know the rules or principles of green chemistry which is used for the calculations or for the understanding of atom economy. There are 12 principles of green chemistry. Number 1 is it is better to prevent waste than to treat or clean up waste after it is formed. Number 2, synthetic methods should be designed to maximize the incorporation of all materials used in the process into the final product. For example, the use of all the reagents or the conversions of all the reagents into the products. Number 3, whenever practicable, synthetic methodologies should be designed to use and generate substances that possess little or no toxicity to human health and the environment. Number 4, chemical products should be designed to preserve efficiency of function while reducing toxicity. Number 5, the use of auxiliary substances, for example, the solvents and separating agents which are used in a chemical process or a chemical reaction, should be made unnecessary whenever possible and when used. Number 6, energy requirements should be recognized for their environment and economic impacts and should be minimized. Synthetic method should be conducted at ambient temperature and pressure. Number 7, a raw material feedstock should be renewable rather than depleting whenever technically and economically practical. Number 8. Unnecessary derivatization, that is the use of blocking group or protection and deprotection groups, temporary modification of a physical and chemical processes should be avoided wherever possible. 9. Catalytic reagents such as selective as possible are superior to stoichiometric reagents. Number 10. Chemical products should be designed so that at the end of their function they do not persist in the environment and break down into degradation products. Number 11. Analytical methodologies need to be further developed to allow for real-time process monitoring and control prior to the formation of hazardous substances. Number 12. Substances and the form of a substance used in a chemical process should be chosen so as to minimize the potential for chemical accidents, including releases, explosions, and fires. Green chemistry, also called sustainable chemistry, as it is a philosophy of chemical research and engineering that encourages the design of products and processes that minimize the use and generation of hazardous substances. Whereas the environmental chemistry is the chemistry of the natural environment and of pollutant chemicals in nature. Green chemistry seeks to reduce and prevent pollution at its source. As chemical philosophy, green chemistry applies to organic chemistry, inorganic chemistry, biochemistry, analytical chemistry, and even physical chemistry. While green chemistry seems to focus on industrial application, it does apply to any chemistry choice. Click chemistry is often cited as a style of chemical synthesis that is consistent with the goals of green chemistry. The focus is on minimizing the hazard and maximizing the efficiency of any chemical choice. Green chemistry has attracted more attention in the past century. Among the 12 principles of green chemistry, only atom economy and E factor can be expressed quantitatively to depict the impact of a chemical process to environment. Atom economy was thought better than the traditional yield for evaluating the atom efficiency of raw materials. But it is not enough to reflect the conversion degree of a raw material. We proposed the concept of real atom economy, which is abbreviated as RAE, as a metric. RAE, or real atom economy, could combine the above two factors together to better express the green degree of a process. We further suggested an equation to correlate E factor with RAE. The concept of RAE is proved to be helpful for estimating an environmentally beginning process. Green chemistry principle, atom economy. Atom economy means maximizing the incorporation of material from the starting material or reagents into the final products. It is essentially pollution prevention at the molecular level. For example, a chemist practicing atom economy would choose to synthesize a needed product by putting together basic building blocks rather than breaking down as much larger starting material and discarding most of its waste. Atom economy is an important development beyond the traditionally taught concept of percentage yield. Barry Trost from the Stanford University published the concept of atom economy in the Journal of Science in 1991. In 1998, he received the Presidential Green Chemistry Challenge Award for his work. At the award ceremony, Paul Anderson, which is the president of ACS in 1997, commented, by introducing the concept of atom economy, Dr. Trost has begun to change the way in which the chemists measure the efficiency of the reaction they design. Atom economy answers the basic questions like how much of what you put into your pot ends up in your products. Atom economy or atom efficiency or atom percentage is the conversion efficiency of a chemical process in terms of all atoms involved and the desired products produced. It is the ratio between the mass of desired product to the total mass of the products, expressed as a percentage. The concept of atom economy and the idea of making it a primary criterion for improvement in chemistry is a part of green chemistry movement that was impulsed by Erastus from the early 1990s. Atom economy is an important concept of green chemistry philosophy and one of the most widely used metrics for measuring the greeniness of the processes or synthesis. Now let's see the step-by-step determination of atom economy. In order to calculate atom economy, the first thing is to write out the balanced chemical equation. Step 2 is to calculate the relative molar masses of each of the product. Number 3, calculate the total mass of all the product. For example, in a reaction of iron oxide in which it is converted into iron and carbon dioxide, the total mass of the iron and carbon dioxide is need to be determined. Step 4, work out which of the following products are wanted and calculate their masses. Finally, apply the formula of percentage atomic economy. Atom economy can be written or calculated as percentage atom economy is equal to the mass of the desired product from balanced chemical equation divided by total mass of the product from balanced chemical equation multiplied by 100. Actually, atom economy gives us the efficiency of a process or a chemical reaction. For example, one of the reaction is carried out in the industry, and we are only interested in the desired product rather than the other products formed during a chemical reaction, which are known as byproducts, which are waste for the industry. Atom economy gives the percentage of the desired product as a percentage of all the products. Higher the atom economy, less is the waste product produced. Now let's see the calculation of atom economy of a reaction with a waste product. For example, industry is carried out a reaction for its desired product, reactant A and reactant B are used for the production of desired product, and along with desired product a waste or byproduct is also formed. In order to calculate the atom economy of a chemical reaction, we must look into the balanced chemical equation and the molecular mass of the reactants and the products. For example, in this reaction, we are going to produce 1,2-dibromomethane. In the production of 1,2-dibromomethane, we are going to use reactant A, which is a bromine, reactant B, which is a ethene. In order to calculate the atom efficiency of a chemical reaction, we must look into the chemical reaction, its balanced chemical equation, and we must know about the molecular masses of the reactants and the products. For example, in a reaction just before you, we are going to synthesize 1,2-dibromoethane. In the synthesis of 1,2-dibromoethane, we are going to use bromine and ethene as a reactant. And in this reaction, only one product is produced. So, we are going to determine or calculate the atom efficiency of a chemical reaction in which only one product is produced, rather the byproducts. In the reaction of 1,2-dibromoethane, the molecular mass of the product 1,2-dibromoethane is 188. Put the value of molecular mass of the product into the atom economy formula, which is atom economy is equal to the mass of the desired product divided by mass of the total product formed multiplied by 100. As in the chemical reaction, the desired product is only one and whose molecular mass is 188, so the formula of atom economy is equal to 188 divided by 188 multiplied by 100, which means that 188 divided by 188 is equal to 1, and 1 is multiplied by 100, so the atom economy of this reaction is 100. In order to calculate the atom economy, let's consider another example of a chemical reaction having byproducts. In the reaction just before you, hydrazine is produced. Hydrazine is used as a famous rocket fuel. It is extensively used in aviation. So in the synthesis of hydrazine, we are going to use ammonia and sodium hypochlorite as a reactant. By the reaction of ammonia with sodium hypochlorite, hydrazine, sodium chloride and water are formed. In this reaction, sodium chloride and water, both these are byproducts, whereas hydrazine is our desired product. So in order to calculate the atom economy, we are going to use the formula of atom economy by putting the values of the molecular masses of the reactant and products. In order to calculate the atom economy, let's have another example of a chemical reaction having byproducts as a waste product. In the reaction just before you, hydrazine is our desired product. So in the synthesis of the hydrazine, we are going to use ammonia and sodium hypochlorite as a reactant. During reaction, hydrazine, sodium chloride and water are produced. On the product side, sodium chloride and water are byproducts and they are not desired by the industry. They are useless or waste for the industry. On the other hand, hydrazine is our desired product. In order to calculate the atom efficiency, first of all, we must know the atomic masses of the elements as well as the molecular masses of the products formed. In this part of the video, we have mentioned the molecular masses of the product. In the reaction just before you, hydrazine has molecular mass 32, sodium chloride that of 58.5, and the molecular mass of the water is 18. So substitute the molecular masses of these products into the formula of atomic economy. When we substitute, then the atomic economy of this reaction is 29.5%, which is not a good atom economy. It means this is insufficient reaction or inefficient reaction, or it is waste for the industry. Now, in this part of the video, we have mentioned the molar masses of the products. In the reaction just before you, hydrazine has a molar mass of 32, sodium has 58.5, and that of the water is 18. Now we are going to substitute the molar masses in the atom economy formula, which is atom economy is equal to the mass of the desired product divided by the total mass of the products. So here the mass of the desired product is 32 divided by the molar mass of the entire products is equal to 108.5. So it means that in the formula of atom economy, which is equal to 32 divided by 108.5 into 100, and the calculations will be equal to 29.5%. So it means the atom economy or the atom efficiency of this reaction, which is just before you, is 29.5%, which is unacceptable. It means this reaction is inefficient to carry out at the industrial scale. So we have concluded that atom economy is a different concern than a chemical yield. because a high yielding process can still result in substantial byproducts. For examples include Cannizzaro reaction, in which approximately 50% of the reactant aldehyde becomes the other oxidation state of the target. The Witting reaction, which uses high mass phosphorus reagent that ultimately become waste, and the Gibberellin synthesis, which produces a stoichiometric quantity of phthalic acid. If the desired product has an enantiomer, the reaction needs to be sufficiently stereoselective even when atom economy is 100%. Diels-Alder reaction is another example of a potentially very atom efficient reaction that also can be chemo, regio, distereo and enantio selective. Catalytic hydrogenation comes the closest to being an ideal reaction that is extensively practiced both industrially and academically. Atom economy can also be adjusted if a pendant group is recoverable. For example, even auxiliary groups. However, if this can be avoided, it is more desirable as recovery process will never be 100%. Atom economy can be improved upon by careful selection of starting materials and a catalytic system. Let's consider another example. That is, the synthesis of an alcohol is readily accomplished by reduction of an ester with aluminium lithium hydride. Lithium aluminium hydride is a reducing agent. It has the ability to reduce the organic compounds. This reaction necessarily produces a voluminous flow of aluminium salts which have to be separated from the product alcohol and disposed of. But the cost of these aluminium salts, which are just behave as a hazardous material, can be considerable. Catalytic hydrogenolysis of an ester is the analogous reaction with a high atom economy, but it requires catalyst optimization, is a such slower process and is not appreciable universally. This radirectional shows the atom economy of different classes of reactions. For example, when atom economy is 0, it means there is no reaction or a totally wrong reaction in which the desired product is not formed. Instead of desired product, there are byproduct or waste products. On the other hand, substitution reactions and elimination reactions, chiral resolutions, stoichiometric reagents, catalytic reactions, and addition and rearrangement reaction, isomerism reactions, which have a definite or specific value of atom economy. On the other hand, addition and rearrangement reaction or isomerization reaction has 100% atom economy. Atom economy of a chemical reaction is a measure of percentage of reactant that become useful products. Inefficient or wasteful processes have low atom economy. Efficient processes have high atom economics, and are important for sustainable development as they are use fewer natural resources and create less waste.